Hello everyone, I welcome you all to this session. Today we will discuss on problems on inverse Z transform by using power series expansion method. In the last classes we discussed about inverse Z transform using partial fraction method. So in that we solved different type of problems and that is solved based on the order of the numerator and denominator. So one more method to obtain inverse Z transform is power series expansion method. In power series expansion method, you have to express x sub z as a power series either in terms of z inverse or z as given in Z transform equation. And the value of the signal x of n are then given by coefficient associated with z to the power minus n. Then based on the ROC, either I write in terms of positive powers of z or negative powers of z. So there are two types of ROC will exist. One is the greater than condition, other one is less than condition. Now the condition is the signal with ROC of the form mod z is greater than a or mod z is less than a. So the two options or two possibilities of ROC. The ROC is mod z is greater than a, then express x of z as a power series in z inverse, negative powers of z, and we get right sided signal. Second condition is the ROC is mod z is less than a, then express x of z as a power series in z, that is in terms of positive powers of z, and we get left sided signal. So this is a power series expansion method, and usually the positive powers of z and negative powers of z will obtain using long division method. So you are dividing the numerator by denominator, then expressing your x of z in terms of positive powers of z and negative powers of z, then comparing with the standard equation of Z transform, you will obtain x of n. Again you are obtaining your x of z is given, and you are obtaining x of n. It is from z domain to time domain signal. And one of the disadvantage of power series expansion method is this only one-sided signal is possible to obtain. We will solve the problems on power series expansion method. The first problem is using long division method, find the inverse Z transform of x of z is equal to 1 by 1 minus az inverse with ROC is mod z is greater than a, and second one with ROC is mod z is less than a. Here the x of z is equal to 1 by 1 minus az inverse. So you know the answer for this with both the ROC, that is mod z is greater than a and mod z is less than a. And if it is mod z is greater than a, you will get the answer as a to the power n into u of n, right sided signal. Another one, if it is less than a, you will get left sided sequence, that is minus a to the power n u of minus n minus 1. But we will solve this problem by using long division method. I will express x of z in terms of positive powers and negative powers of z. The first condition with ROC is mod z is greater than a. Since ROC indicates that x of n is a right sided, so you know that when it is greater than the greater than condition, ROC x of n is always a right sided sequence. This is one of the properties of ROC. Now to apply a long division method, I am just dividing the numerator by denominator. So I will take 1 here and I will take 1 minus az inverse. Then I'll consider here this as 1 and I'll multiply 1 into this divisor. You get answer as 1 minus AZ inverse minus plus, so this get cancelled, so you'll get AZ inverse. The second term I'll take AZ inverse, I'll multiply by this particular term to the divisor, then AZ inverse plus into minus a square z to the power minus 2. Again minus plus, so this get cancelled, so you get a square z to the power minus 2. Then I need to cancel this, so I'll consider a square z to the power minus 2. I'll multiply to the divisor, so I'll get a square z to the power minus 2 minus a3 z to the power minus 3 minus this is plus, this get cancelled, so you'll get a3 z to the power minus 3. So this continues. I'll stop it here and I'll just write this quotient. The quotient is as x sub z. It is x sub z is equal to 1 plus az inverse plus a square z to the power minus 2. Then the next term will be a3 a to the power 3 into z to the power minus 3. It continues till infinity. Now if I write in a standard form, I mean in terms of in general form, then I can write it as summation n from 0 to infinity a to the power n z to the power minus n. If I put n is equal to 0, I'll get a to the power 0 z to the power 0 1. If I put n is equal to 1, I'll get a into z inverse. If I put n is equal to 2, I'll get a square into z to the power minus 2. And here, the limit is from 0 to infinity. So therefore, this is a right-sided sequence. Then this equation I'll compare with the standard equation of z transform, that is x of z is equal to summation or n is from minus n plus infinity x of n z to the power minus n. And if I'll compare this is my x of n, right? This is my x of n. So I'll write therefore x of n is equal to a to the power n, and this limit is 0, lower limit is 0, and the upper limit is infinity. So I'll write multiply the u of n. So I'll get the answer as x of n is equal to a to the power n u of n. So this is answer for with ROC's mod z is greater than a. Now second condition with ROC's mod z is less than a. Yeah, since ROC indicates that x of n is a left-sided sequence, because the less than condition is always for a left-sided sequence, now we have to write the numerator and denominator in the reverse order. Here also I'll apply a long division method only, but I'll write the numerator and the denominator in the reverse order. Then I'll multiply with the following terms. So I'll write 1. If there is no changes, because in the numerator only 1 is there, and the denominator, I mean the divisor, I'll write it as minus az inverse plus 1. So I'm not changing the sign, very important thing. I'm just writing in the reverse order. Earlier it was 1 minus az inverse, just write it as minus az inverse plus 1. Okay, now I need to cancel this 1. For that I need to multiply the minus a inverse into z for the divisor. If I'll multiply this particular term, I'll consider minus a inverse into z. A it cancels and even z it cancels. We'll get the answer as 1. So 1 minus into minus it is plus 1. And again I'll multiply this to 1. Then I'll get minus a inverse into z. So minus plus this get cancels. Get this is plus a inverse into z. Next I need to cancel this. So I'll consider the quotient as minus a to the power minus 2 z square. So I'll multiply this to the divisor. So I'll get minus a square into this. So I'll get minus a inverse. A z square is z to the power minus 1. So it is z. And again I'll multiply this minus a to the power minus 2 z to the power 2 minus plus this get cancels. I'll get a to the power minus 2 z square. Again I'll put minus here plus this get cancels. Here I'll get a to the power minus 3 z cube. Now I need to cancel this. So I'll consider minus a to the power minus 3 z cube. I'll multiply this. So here a to the power minus 3 into this. Yeah, this is got already taken minus a to the power minus 3 into z cube minus a into z inverse plus 1. I'll get a to the power minus 2 z square minus a to the power minus 3 z cube, and this get cancels. I'll get the answer as a to the power minus 3 into z cube. Continue in the same fashion. You can observe here you'll get the powers of z in positive, that is z square, z cube, z to the power 4 and all. Now I'll write this quotient as x of z. So x of z is equal to minus a inverse into z minus a to the power minus 2 z square minus a to the power minus 3 z cube minus a to the power minus 4 z to the power 4 and so on. Now in general I can write this as summation over n is from minus infinity to minus 1 minus a to the power n z to the power minus n. Right, the last term I'll get here, that is z to the power minus infinity z to the power minus into minus z to the power infinity. So I can write this as the lower limit as minus infinity, upper limit as minus 1. I can write minus a to the power n z to the power minus n. And here based on the limit you can identify this as a left sided sequence. Right? Because this is valid for n less than 0. So this is a left sided sequence. Therefore, if I'll compare with the standard equation, I can write x of n as, here this is my x of n, minus a to the power n, and because of this limit minus infinity to minus 1, I'll multiply u of minus n minus 1. So this indicates it is a left sided sequence. Therefore, for ROC mod z less than a or less than condition is there, then always your x of n will get left sided sequence. And the important thing is here, while dividing the numerator and denominator, you just write in the reverse order, then you just divide. So all you'll get in terms of positive powers of z. And this is applicable for all type of problems with the ROC for greater than condition and less than condition. Just dividing the numerator by denominator, writing the x of z in terms of powers of z, the negative powers of z or positive powers of z. If it is a negative powers of z, right sided sequence. If it is a positive powers of z, left sided sequence. The next problem. So this is using long division method, find the inverse z transform of x of z is equal to 2 plus z inverse divided by 1 minus 0.5 z inverse. With ROC mod z is greater than 0.5. So this question is appeared in a model question paper. So I'll write here x of z is equal to 2 plus z inverse divided by 1 minus 0.5 z inverse. And here you can note down the ROC. ROC indicates that x of n is a right sided sequence because here the given mod z is greater than 0.5. So I'll divide the numerator by denominator, and so I'll write as it is the numerator and denominator. So this is my divisor, this is my dividend, that is numerator 2 plus z inverse divided by 1 minus 0.5 z inverse. First I'll take 2 here, I'll multiply into this divisor, so I get 2 minus z inverse, 2 into this, 2 into 0.5 z inverse, so I'll get minus z inverse here. This get cancels, we'll get 2 z inverse. Next I'll take 2 z inverse, I'll multiply to this, plus 2 z inverse minus z to the power minus 2 minus plus, this get cancelled, so we'll get z to the power minus 2. Next I'll take z to the power minus 2, I'll multiply to this, z to the power minus 2 minus 0.5 z to the power minus 3 minus plus, I'll get 0.5 z to the power minus 3. So I'll continue in the same fashion, I'll get in terms of negative powers of z, z to the power minus 4, z to the power minus 5 and so on. Now I can write this as x of z, so x of z is equal to 2 plus 2z inverse plus z to the power minus 2 plus 1 by 2 z to the power minus 3 plus so on. So thus we can write, or thus we can conclude that the x of n is equal to 0 for n less than 0, because I got the power in terms of negative powers of z, and when it is a negative powers of z, generally we'll get right-sided sequence. Therefore, I can write x of n is equal to 0 for n less than 0. And then I'll just compare the coefficient of x of z. So here the coefficients are there. Here this is x of 0. I write x of 0 is equal to 2. This is x of 1. So x of 1 is equal to 2. Then x of 2 is 1. X of 3 is 1 by 2. Sorry, this is 1 by 2. So x of 3 is 1 by 2. Therefore, I'll write x of n is equal to, if I take the inverse transform this equation, then I'll get 2 into delta of n, because you know that z transform of 1 is, z transform delta of n is 1, and z transform 1, inverse transform of 1 is delta of n. So therefore I can write this as x of n is equal to 2 into delta of n plus 2 into delta of n minus 1 plus delta of n minus 2 plus 1 by 2 into delta of n minus 3, and so on. So this is inverse transform of given x of z. So in this problem they are given the ROC is mod z is greater than 0.5. So the one more possibility is with the ROC is mod z is less than 0.5. So that also you can obtain. We'll consider the second condition. Note, if ROC is mod z is less than 0.5, this indicates that x of n is a left-sided sequence. So we have to write the numerator and denominator in the reverse order, then apply long division method. So I'll write the numerator and denominator in the reverse order. This z inverse plus 2. So earlier it was 2 plus z inverse. I write z inverse plus 2, and the denominator I write minus 1 by 2 z inverse plus 1. So I need to cancel this term z inverse by using this divisor. So I'll consider minus 2. So minus 2 into this. So this 2 to get cancelled. So you'll get minus into minus is plus z inverse. Again minus 2 into 1. So you'll get minus 2. So this is minus, this is plus. This get cancelled. So you'll get 4. So next I'll take to cancel the 4 by using this particular term. I'll take minus 8z. So 8 into this. So 8 by 2 is 4. Minus into minus is plus 4. Z and get cancels. Z inverse and Z get cancels. You get 1. So 4 minus 8z. So 4 is minus, this is plus, this get cancels. You get minus 8z. This is plus, so 8z. So next I need to take, need to cancel this 8z. So I'll consider minus 16z square. Minus 16z square into this. So minus into minus it is plus. So 16 by 2 is 8. Z square into z inverse is z. And here it is minus 16z square. So the 8z minus 16z square minus this is plus, this get cancels. You get 16z square. Next term will be minus 32z to the power 3. Next will be, that is in terms of 2 to the power. You can observe here 4 you can take. So 32z to the power 3 and so on. Therefore x of z I will write it as minus 2 minus 8z inverse, sorry, minus 2 minus 8z minus 16z square minus 32z to the power 3 plus so on. As I can write, by looking at this equation, you can write the x of n is equal to 0 for n greater than 0, because there is no negative power sub z. Right, there is no negative power sub z, and but here this one is I can take this as x of 0, and this is your x of minus 1. This is x of minus 2. This term is x of minus 3. So therefore I will write x of 0 is equal to minus 2. X of minus 1 is equal to minus 8, x of minus 2 is equal to minus 16, x of minus 3 is equal to minus 32. Therefore x of n can be written as, if I take the inverse transform of this particular term directly, then I can write minus 2 into delta of n because you know that the transform of delta of n is 1 and the inverse Z transform of 1 is delta of n. Minus 8 into delta of n plus 1, because this is multiplied with positive z, and the delta of n plus 1 Z transform is z, and delta of n plus 2 is Z transform z square. So here it is shifted to the left side, so then the signal will be delta of n plus 1 minus 16 into delta of n plus 2 minus 32 into delta of n plus 3, so on. So this is my x of n by taking the inverse Z transform of this equation. So this is the answer, or you can write directly the coefficients only, x of 0, x of minus 1, x of minus 2, x of minus 3. So here also you can observe one is in terms of negative powers of z, another one is in terms of positive powers of z. So again it depends upon the ROC. If the ROC is mod z is greater than condition, always you will get negative powers of z. If it is in less than condition, you will get in terms of positive powers of z. Next we will consider some the standard equation and the power series expansion of some of the standard signals. That is exponential term, sinusoidal term, then log, 1 by 1 minus x. And this series, here you use a Taylor series to write this power series expansion. We consider e to the power x. So e to the power x is given by 1 plus x square divided by 2 factorial plus x cube by 3 factorial plus so on. This can be written in terms of summation as summation n from 0 to infinity x to the power n divided by n factorial. As you already studied in your mathematics, the power series expansion of some of the standard signals. So this can be given as n is equal to 0 to infinity x to the power n factorial. The second equation sin x. Sin x is given by x minus x cube by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial and so on. And this can be written as summation n over 0 to infinity minus 1 to the power n x of x to the power 2n plus 1 divided by 2n plus 1 factorial. And here if I go and put the values of n, that is n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3 and so on, we'll get this expression. So this is in standard form or in general form, minus 1 to the power n x to the power 2n plus 1 divided by 2n plus 1 factorial. Similarly, the cos term is cos x is equal to 1 minus x square divided by 2 factorial plus x to the power 4 by 4 factorial minus the continuous like this. Then generally you can write this as summation n is equal to 0 to infinity minus 1 to the power n x to the power 2n divided by 2n factorial. Generally the cos you will get even terms and the sine you will get odd terms. It is odd powers of x, 1, 3, 5, 7. Here you will get 0, 2, 4 and all. The next one more important power series is 1 by 1 minus x. 1 by 1 minus x. This can be written as 1 plus x square plus x to the power 3, so on. This can be written as I can write this as n is equal to 0 to infinity x to the power n. So this can be written as 1 minus x inverse. Expand it, I'll get this particular equation. And in general I can write this as summation n from 0 to infinity x to the power n. Then fifth one is natural logarithm of 1 plus x. So this is equal to x minus x square by 2 plus x to the power 3 by 3 minus, and this can be written as summation n from 1 to infinity minus 1 to the power n plus 1 x to the power n divided by n. And one more is natural logarithm of 1 minus x, that is ln 1 minus x is equal to minus x square by 2 minus x3 by 3 minus, you'll get all in negative terms, equal to minus of summation or n is equal to 1 to infinity x to the power n divided by n. So this is the power series expansion of some of the standard signals. Power series expansion of some of the standard signals. And now if you are able to remember these equations, that is e to the power x sin x cos x 1 by 1 minus x, and here you can observe here the power I written in terms of powers of x. So instead of x, you can expect the problem in terms of z. Suppose an example is e to the power z or e to the power z inverse. So then you have to express this equation, that is e to the power z. I can write 1 plus z squared by 2 factorial plus z to the power 3 by 3 factorial. Or generally I can write this as n is equal to 0 to infinity z to the power n divided by factorial. That way you can write. So this, if you are able to remember this equation, then you can solve the problems on different power series expansion of some of the standard signals. It is sine, cos, log, then e to the power, exponential terms and all. So find the inverse Z transform of x of z is equal to cos 2z. One problem, cos 2z. Other one, x of z is equal to e to the power z square. Now the first problem is I'll take x of z is equal to cos 2z, and you know that using power series expansion of cos x, the cos x is equal to 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial minus is equal to summation over k is equal to 0 to infinity minus 1 to the power k x to the power 2k divided by 2k factorial. So I written here k because I am obtaining x of n. To avoid the confusion, I write in terms of k. K, the summation is parameter I used, variable is used k instead of n. Now instead of x, I will substitute 2z here. This cos 2z, 1 minus 2z whole square divided by 2 factorial plus 2z to the power 4 by 4 factorial and continuous. Therefore, this can be written as summation k from 0 to infinity minus 1 to the power k 2z to the power 2k divided by 2k factorial. So I'll write this, I'll expand this. Therefore, x of z is equal to summation over k from 0 to infinity minus 1 to the power k 2 to the power 2k into z to the power 2k. I'll expand this 2 to the power 2k by z to the power 2k divided by 2k factorial. So I'll take all the constant term, I'll write as it is, and wherever z is there, I take the inverse Z transform of this. I know that the inverse Z transform of z is delta of n plus 1, right? So and here z to the power 2k is there, the power is 2k. So I using a time shifting property, I can write this as its inverse Z transform is delta of n plus 2k. Suppose if it was a negative power here, then I should write it as n minus 2k. Therefore, x of n is equal to the summation over k from 0 to infinity minus 1 to the power k 2 to the power 2k divided by 2k factorial. The answer is delta of n plus 2k. So this is my x of again for cos 2z. The second problem is the x of z is equal to e to the power z square. Consider that x of z is equal to e to the power z square. Now using power series expansion of e to the power x, you can write e to the power x is equal to 1 plus x square by 2 factorial plus x to the power 3 by 3 factorial plus in general I can write this as summation of k is equal to 0 to infinity x to the power k divided by k factorial. Now wherever x is there, I will just replace by z square. E to the power z square is equal to 1 plus z square to the power 2 divided by 2 factorial, z square to the power 3 by 3 factorial. Generally I can write summation of k is equal to 0 to infinity z square to the power k by k factorial. The x of z is equal to summation over k is 0 to infinity z to the power 2k divided by factorial. So I'll take the constant term outside, that is 1 by k factorial, summation over k from 0 to infinity. Take the inverse transform of this. The inverse transform of this is delta of n plus 2k. So here the very important thing is, if we know the power series expansion of the standard signal, just expand this, then write in a general form, then take the inverse transform. Now here also you can observe that is either in terms of negative power sub z and positive power sub z will be there. So we'll find x of n using a power series method. If x of z is equal to 1 by 1 minus 4 z inverse, the mod z is greater than 1 by 4. The ROC also mentioned here. And I can express this or write x of z in terms of power series, so it is infinite series. And you can observe this equation, they are 1 by 1 minus 4 z in 1 by 4 z to the power minus 2 with ROC's the magnitude of z is greater than 1 by 4 is given. And if I use an infinite series expression, I can write this directly as x of z is equal to k from 0 to infinity, the summation from k from 0 to infinity, 1 by 4 z to the power minus 2 to the power k. And if I'll use the infinite power series expression, I'll get this 1 by 1 minus 1 by 4 z to the power minus 2. So I can directly write 1 by 4 z to the power minus 2k. Now comparing with x of z equation, your standard x of z equation, that is x of z is from minus infinity plus infinity, x of n z to the power minus n. Right? I can write x of n is equal to summation over k is from 0 to infinity, 1 by 4 to the power k, this is a constant. Remaining is z to the power minus 2k, right? Z to the power minus 2k. And the inverse transform z to the power minus 2k will be given by delta of n minus 2k. So this is enough. This is my x of n. Or I can write this as x of n is equal to 1 by 4 to the power n by 2, with n is equal to even and n is greater than or equal to 0. For n anyway, for n less than 0, this answer is 0. For n is greater than or equal to 0 and n is even, you'll get 1 by 4 for n by 2. And it's 0 for n is equal to odd. So this is the answer. One more way I have to represent x of n. Or you can write x of n is equal to this particular equation. So this is a Z transform of the different signal by using power series expansion method. So either power series expansion method involves the long division method also. The important thing is here I am expressing x of z in terms of positive powers and negative powers of z based on the ROC. Either greater than condition or less than condition. If it is greater than condition, I'll get negative powers of z. If it is a less than condition, the ROC, I'll get positive powers of z. That is right sided sequence and left sided sequence. So this is about inverse Z transform. One more method to obtain the inverse Z transform.